Okay, so lecture number 20. Today we'll be talking about an introduction to neural networks. I realize that neural nets have gotten so popular in the last few years that probably everyone has studied them in some form or another. But what we're going to do is go really from the ground up with the theory as to why they work, not just how and like implementation and stuff. So hopefully you'll still learn something. So I've got a bunch of slides to go over, and then I'm going to give a demo, a nice demo from the Tensorflow Playground website, which will illustrate a lot of these things that we've talked about throughout the lecture. And then at the very end, I've made some changes to assignment 5, and I posted about that on D2L, but I just want to go over that quickly, spend like maybe 5 or 6 minutes at the end to make sure that everything I said is understandable. Okay, so lecture number 20, Intro to Neural Networks. So a really quick, fun story that I like to tell about neural nets pre-2012, which I'll talk about in a second, is so whenever I make lectures for classes like this, I like to go look at other AI class lectures that are available. So for example, there's like MIT OpenCourseWare, Stanford puts some stuff out, Waterloo puts some stuff out, Berkeley puts some stuff out, etc. And I just happened to be watching like 5 years ago or so, I was watching the Intro to Neural Nets part, I think, of the MIT Intro to AI course. And the guy was saying, the prof was saying that in 2010, MIT was reviewing what topics it should drop from its AI course to make room for more modern and not only more modern, but more effective techniques. And it turned out that neural nets in 2010 were about to be dropped from the MIT Intro to AI course. Now, a bunch of stuff have been done with neural networks. They've been around since the 70s, 80s, 90s. They've been like really great for image classification stuff, like especially handwritten digits. So they had some success. But in about the dozen years or so before this, really not a lot of improvement had been made in the field of neural networks. And so in order to to update the course for more modern techniques and stuff, they were actually thinking about dropping neural nets. And it turned out they decided to leave in neural nets in the course just because it was kind of interesting to show how this model of an artificial neuron could somehow be related to how the human brain thinks about stuff, etc. So I just think that's really funny, knowing what we know now about how things turned out, that there was a point not too long ago when neural nets were kind of considered old-fashioned and not really performing very well. So in almost 30 years, this is kind of unfair. I should update that. Not fail to yield any significant results, but in the few years prior to this, there hadn't been a lot of gain in what they were able to do. Then, in 2012, along came Geoffrey Hinton and his research group at University of Toronto, and we'll talk about deep neural nets a little bit in the next lecture, so what they are, just ignore that for a bit. But in 2012, ImageNet classification with deep convolutional neural networks, and we'll talk about what convolutional neural networks are. So there's this ImageNet classification competition, and in 2012, Geoffrey Hinton realized that if you just take neural networks and you apply massive computation to them, that's all they needed to go to the next level, and nobody had tried it before that. And so in conjunction with convolutional deep neural networks, throwing these onto GPUs and just having like millions and millions of parameters, it turns out that's what neural networks needed to be really super powerful. So they had 60 million parameters in the network, and this competition was given 1,000 different categories of pictures, try and classify these pictures into one of the categories. And this blew away the competition in a massive way. And so here's just an example from this where they had they were successfully able to classify all of these images, and we'll go into that a bit in the next lecture. And since then, there's been a tremendous amount of success, and these slides are actually kind of old now. I'm not even mentioning any of the stuff with ChatGPT or large language models, but just specifically for games, for example. In 2015, Google DeepMind created this AlphaGo program, which was able to play Go, which was a notoriously hard game to play for computers, and was able to beat the world champion. And then shortly after that, the poker AI team at the University of Alberta, so this was actually taken while I was there, so some of these guys were in the same lab as me, so that was really cool. They were able to essentially solve limit heads-up poker, which hadn't been done before. And they've made great strides in no-limit heads-up poker and stuff since then. So what is it about neural networks that makes them tick? You know, like, this is how most of the world looks at a neural net probably right now, right? Okay, we have some inputs and then some sort of miracle occurs and the output is there. But it turns out they are not a miracle, right? Everything is just mathematics. It turns out that this mathematics, when you apply massive computation to it, ends up being really, really powerful. So just a quick, I like this slide because it kind of compares the computer's hardware to the brain's hardware. And not to say that, you know, if they were all the same, we'd be able to do the same things. They fundamentally work in slightly different ways, obviously, but still it's a cool thing. So in a computer, you know, a typical high-end consumer-grade computer has on the order of billions of transistors in it, whereas the brain has a couple of order of magnitudes more neurons than we currently have in transistors. But of course, if you get a supercomputer of like tens of thousands of computers linked together, then you'd probably get on the same order as the number of neurons in the brain. In computers, we may have up to, like, let's say, you know, modern servers may have a couple of terabytes of memory, meaning RAM, not storage. Whereas in the brain, we have a bunch of neurons and synapses, which are still a little bit bigger than, you know, obviously than the amount of storage that someone like Amazon has. It's probably bigger, but a typical computer wouldn't have as many bytes of information in RAM as synapses in the brain. Processing speed is very, very quick, on the order of billionths of a second. We have gigahertz. Gigahertz literally means billions of things per second. But the brain, its processing speed is far slower per calculation. Or not necessarily calculation, like your brain doesn't have a sine function or something like that. It's, you know, message passing in the brain, synapses firing, etc. But the bandwidth for modern computers in terms of how fast they're able to pass data around is far slower than what the human brain is able to do, because the brain is just so massively parallel. But this slide is a few years old, and of course, you know, Moore's law, it's increasing all the time, so we may surpass the human brain in every way in years to come. This is a schematic of a biological neuron. So the brain is made up of neurons and synapses, and the neurons connect together in interesting ways. I'm not about to try and explain the physiology of the brain or the biology of the brain, nor will there be any sort of question on the exam about this, but I'm showing this diagram so that later, when I show a diagram of an artificial neuron that we're going to use in neural networks, you can kind of get the sense that, yes, these two things are related in some sort of way. So the biological neuron has these, and, you know, biological neurons aren't orientated from left to right, obviously, but that's the way we're going to look at it. There are input electrical signals that go into these dendrites at the beginning of a neuron. And then there's this sheath which has axons in it. And based on these signals, there are electrical signals that fire, and then we get outputs from these signals. And the thing is, in the brain, the output signals from neurons are somehow connected to the input signals of other neurons. And so we do have these networks of neurons in the brain that are firing and figuring things out. And so that's all I'm going to say about this, and it's only so that we have the biological motivation for why artificial neurons were introduced and neural networks were introduced. And turns out they're pretty powerful. So the neuron, axons from one neuron extend to the dendrites of another neuron, and stimulation of the dendritic tree of a neuron may cause the axon to spike like a transmission in a line. And after firing, the neuron will go quiet for a while, so there's a refractory period in the neurons, and then this firing can affect surrounding or connected neurons and form this sort of chain reaction. So we have input signals, some sort of, what did I call it, pulse, and then output signals, which go to the inputs of other things, of other neurons. So before we get into the modern artificial neuron, I want to start back at the beginning, because I think this is what really sealed the deal for me and made me understand sort of how neural networks work. And the very first form of artificial neuron was called a threshold logic unit. Has anyone heard of a TLU before? Okay, good, because I didn't know it before I looked it up for this course either. So a threshold logic unit, here's a diagram of one down here. And the parts of a TLU are the inputs, x1 through xn. And for a TLU, this very first basic form of artificial neuron, all of those inputs are just binary. So they're all ones or zeros. And then there is this other variable, and these are W, or these are weights, right? So these are all real valued, and we can think of these things as vectors, right? So we have a vector of binary inputs and a vector of weights. And then the inputs are multiplied by the weights and then summed together. So down here, we have from I equals 1 to n, wi times xi. And remember, these xi's are either ones or zeros. And so if that sum is greater than some threshold that we put into the TLU, that's the last parameter, then the output is 1, otherwise it's 0. And so multiplying x1 by w1 plus x2 times w2 all the way up to xn times wn, who knows what the name of that mathematical operator is? If you do this, if you sum the multiplication of the individual elements of two vectors, a certain type of product, dot product, good. So essentially, if the dot product of the x's and the w's is greater than a threshold, we get 1, otherwise we get 0. And you're saying, okay, what the hell can that do? Right? Like, that's interesting, but what can it do? Well, we'll have a look. So by choosing different values for the weight vector, we can have a TLU compute the output of different functions. Oh, that's interesting. So this can be a function approximator. So let's look at some logical operators that we can approximate or actually do perfectly with threshold logic units. So the first one up here is the Boolean operator AND. So can we use a threshold logic unit to mimic the behavior of the AND operator with two inputs? So what we have to do is we have, here we're going to just use two inputs for this because it's x1 and x2. So we have two x's which are Boolean, either 1 or 0, and then we have some weights, and we have a threshold. So what we'll do here is we'll see if we can find some values for the weights and the threshold such that any possible input we would give for x1 and x2 actually yields the AND of those two Boolean variables. Okay, so here I'm not going to go through. You would just find these through some method, but here are some values that does that. So if we take 3 as the weight for x1 and 2 as the weight for x2, then we have the function 3x1 plus 2x2. That is the dot product of those two vectors. Then, if we choose the variable 4 for our threshold, what we'll do is we'll compute 3x1 plus 2x2, and if that value is greater than 4, then the output is 1. If not, then the output is 0. So we can see here, let's just go over, you've all done truth tables before, it's really simple. So let's go over all the 4 possible input values to this function, because there is 2 values and each of them can be a 1 or a 0, so we have 4 possible. So if we take 0 and 0, 3x1 plus 2x2 is 0, which is not greater than 4, so it's 0. Similarly, 3x1 plus 0x2, 3 times 1 plus 2 times 0 is 3, which is not greater than 4. The next one would come out to 2, which is not greater than 4, but the last one would come out to be greater than 4, right? So, and apologies to anyone who's watching on the video only, because my face is probably going to be covering up this. Maybe I'll try and edit it out if it's not too much work. But there's a black dot up here, and the black dots are essentially 1s, and the white dots, or the non-filled dots, are going to be 0s. So if we draw a plane, because we have 2 variables, right? So this makes a 2-dimensional space. Each of those have 2 possible input values. So x1 has 0 or 1 as an input value, and x2 has 0 or 1 as an input value. So if we draw these, so if it's 0 and 0, it's 0, 0 and 1 is 0, 1 and 0 is 0, but 1 and 1 is 1. So in this 2-dimensional space, the function 3x1 plus 2x2 greater than or equal to 4 is what sort of shape? You've all seen y equals mx plus b before. What is that the formula for? A straight line, right? So what we've done is the threshold logic unit with the proper variables forms a line in this two-dimensional space which classifies the zeros from the ones. See how that works? So we've drawn this line here. So this is the variables 3 for the weight for x1, 2 for the weight for x2, and 4 for the threshold, literally is this line, which cuts the space in two, and if that cutting of the space in two separates all the 0 inputs from the 1 inputs, then we have correctly made a classifier that is able to output this function. So that's really cool. And if a function like AND is able to be separated with a single line, then that's called linearly separable. Okay? So linear separability is the ability to cut this function and classify its outputs with a single line in a space. Let's look at another one. So here we have a TLU for implication. So implication is another logical operator. X2 implies X1. I won't go through all the calculations again because I'd just be repeating basically what I just said. But if we take the weight 2 for X1 and negative 2 for X2, and then we calculate that, if that is greater than negative 1, the output is 1. If it's not, then the output is 0. So here we have a case where the only 0 is when we have 0 for X1 and 1 for X2. And so this formula is able to classify the ones from the zeros by drawing this line through the plane. Okay? So if I can draw a line through the plane to separate them, then a very simple TLU is able to replicate that function, and that function is called linearly separable. Let's have a look at another slightly more complex example, because these 2D examples are really easy, but TLUs can be used to compute functions for any number of variables, right? So here we have a really complex function. I'm not even going to bother reading it out or bother going through this, but just to let you know that if there are 3 variables, then we have a 3D space. And so what the TLU is computing there is the function for a plane through that 3D space, right? So we have an n-dimensional space. The TLU is going to give us an n-1 dimensional separator or classifier through that space. And it just so happens that this particular function is linearly separable with a plane through a 3-dimensional space. So we're talking about, and so this is what essentially neural networks are at a very, very low level. It's a bunch of chopping things up in a space so that we can separate them, okay? And I'll get to that when we talk about neural nets, but this is really, it's pretty cool how they work, in my opinion. So we call 2 points in an n-dimensional space linearly separable if they can be separated by an n-1 dimensional hyperplane. That's just a fancy way of saying if it's 3 dimensionals, it's a plane. If it's 2D, it's a line, etc. One of these sets may contain points on the hyperplane. So it may be right on one of those points, right? So it doesn't need to be like absolute separable. It can be on the point as well. A Boolean function is called linearly separable if the sets of points of 0 and the sets of points of 1 are linearly separable. Okay, so consider this function. Consider the by implication problem. That's, I guess, the philosophy way of saying it, but equality, right? So the equality operator, there is no separation line. Look at this graph. Could I possibly draw a line through that graph to separate both the zeros and the ones? No. Right? Because no matter where I draw it, there's always one or the other on the same side. Okay? So there is no way to form a TLU to be able to compute the equality function. Now, it turns out later on we can see that maybe we could have multiple TLUs chained together to be able to do this, because if we were able to draw multiple lines, then we could draw, say, for example, a line here and a line here, and then we have outside of those are ones and inside are zeros. But now, for now, we're just talking about single things. And it turns out that for Boolean functions, the number of linearly separable ones are few, and there are very few, right? There are not many of them. And so there are far more non-linearly separable functions than there are linearly separable ones. Turns out that for 2 inputs, there would be 16 possible Boolean functions, 14 of which are linearly separable. So that equality operator is one of the only ones that isn't. And I think XOR is the only other one that isn't, right? Because anything where you have like the two opposites, you couldn't draw a line between them. So equality is one and not equal is the other one. So it may be a question on an exam is if I give you a function, a simple one like this, come up with the truth table and the variables for this to compute a TLU to separate those things, right? It sounds kind of difficult, but it really isn't hard to come up with those numbers. So for many inputs, TLUs can't compute those functions. And so networks or combinations of TLUs would be needed to overcome this. And so that's a little bit of foreshadowing for the future. But TLUs aren't what we use nowadays. We use neurons or artificial neurons. And the first form of artificial neuron, which was like one step up from a threshold logic unit where we had binary inputs, would be the perceptron. So the perceptron, this would be the fundamental unit of early neural networks. And so what we have here is instead of Boolean inputs, we have real valued inputs. Ignore this one for right now. I'll talk about that, what that is in a second. Then we have those real valued inputs multiplied by real valued weights. So we multiply those together and we sum them. So this is this operation. Then we have what's called an activation function. So in our previous example of threshold logic units, we were computing this dot product and then just checking to see if it's greater than something, the output is 1, otherwise the output is 0. So that's what this activation function is, okay? So we would say the output is 0, this bottom line, if this condition is true, otherwise the top line is a 1 if that condition is not true, or the opposite of that. So this is a step function, and this will be important later. So that activation function is what determines the output. We take a dot product, we do this comparison, which is this step function, and then we get our output. And we can see now that this sort of looks like this actual neuron, right? We got the inputs over here on the left, we got an output over here, and we got some magic going on in the middle. That's as much as I'm really going to say about it. And then, if we want to take a very, very simplified model of the human brain, right, we have a bunch of these things put together in some sort of network. Now, we know on a micro scale what that looks like, but we still don't know, exactly what's going on in the brain. We don't have a full model of it. We don't have the computational power to fully simulate the brain. But on some level, what we have are a bunch of inputs. And then in here, we have some network of real neurons. And then our output vector y is going to be some function of these inputs, okay? So what they did back in the, 50s or 60s, whenever this was first thought about, was they said, let's put a whole bunch of these artificial neurons together to form what we call a neural network. So the parts of a neural network that we're going to be focusing on, we have these inputs, right? So we have these x inputs, they are real valued. Then we have weights that are going on those. And then on the output, on the other side, we have the outputs. So for example, we may have a single output. If we're trying to learn the value of a single function, maybe this is a single output. If this is a classifier where we're trying to predict whether or not it's an apple or an orange or a pear, then we might have 3 outputs with a value between 0 and 1 with how certain we are about those things. But the output has some structure. And then what we have are these intermediate nodes. And what we do is we separate these into layers. So this would be like layer 1, layer 2, layer 3, each of those consisting of some number of neurons. And in its most basic form, this is called a fully connected network. And it's called fully connected because the output of each layer feeds into the input of every future layer. These are often called hidden layers because what they do in the middle doesn't really matter because it's just like a black box, right? So we feed in inputs, it does the learning, and then we get the outputs. And so that's the structure of a model, a modern neural network. Now, of course, we can do all sorts of crazy optimizations and other things on top of this, but in its most basic form, this is a fully connected neural network. And so the whole point of a neural net is that we have some inputs, and what we want to do is find the weights for all of these, such that the output is what we want, right? And this happens not only at the input layer, but each of these inputs as well, okay? So we would have the output from this neural network, which is a function of its inputs and its weights, be the inputs for the next neuron in the next one. And if all of the ones from this layer, so you can see here, this one has 4 inputs because there were 4 in the layer before it, we are trying to find all of these weights. So when we looked at Geoffrey Hinton's deep neural network and it had 60 million parameters, these are the parameters that it's talking about. And now you can see how just a small network can have even thousands and thousands of parameters, okay? So how do we go about actually training one of these neural networks? How do we find all those weights? Because it would be a monumental task to try and set all of those by hand. So given that we have some input data and some known outputs, so typically training a neural network is a supervised learning task. We're going to have some inputs with known values, right? And remember we talked about this part of supervised learning before. It's going to go through some process of updating its internal weights based on the errors, and that's going to tune those weights to produce the correct values. So running inputs through the network gives us some calculated values. So this y bar just means that it's a vector, okay? So we have some vector of outputs, which is a function of the vector of inputs, the vector of weights, and the vector of thresholds, because we're still dealing with the thresholds of this perceptron. We haven't moved on to a truly modern neural network yet. So training a neural network involves tuning the weights. So the act of putting inputs into a neural network, it calculating all those dot products and then coming up with an output, that one calculation is called feed forward, all right? Because we're taking the inputs, we're feeding them into the neural net, and then we feed them forward, okay? What we'll see in a bit is this other process called back propagation, where based on the error values of our predictions, we then update the weights back through the neural network. So there's feed forward and back propagation. So training a neural net involves tuning the weights and thresholds of the values to get the network to match our training data as much as possible. And so really, a neural network is what we call a function approximator. It is approximating some function. And as we tune the values and the parameters of that network, our function is getting more and more accurate with respect to the real function that we're trying to mimic. So here's just a quick look at an animation at what happens here. So in a neural network, we have some inputs. They get fed into the neural network. So this is the feed forward part. I hope this loops. So we feed forward. Then we get some function. We compute the loss or the error. And then based on that loss, this process of back propagation happens, where based on that error, we tune each individual weight to try and get closer to the true value. Okay, so that's what's happening when we train a neural network. We're not going to get too much into the math, but I do want to talk about it just a little bit. So the training progress looks sort of like this. We have some desired function d bar, okay? So that's the function that we want. And that is some actual function, like if we were some omnipotent oracle, we would have this function g, and so the actual function depends only on our inputs, right? If we had the true function that, God spoke to us, what is the function on these inputs, then all we would need is just the inputs. So give me the inputs. Yep, question?
Is this like H star or pi star from the other sections?
No, that was talking about optimal stuff. This is something completely different. Yeah. So this is, there's a function we want to approximate, right? So that function could be x squared. It could be this is an apple or an orange. It could be how to play checkers, right? That function is just unknown to us and we're trying to approximate it. But what I'm trying to say here is, in reality, all you would need for that function, if you had this oracle function, would be the inputs. But the neural net function is not just a function of inputs. It is a function of the inputs, the weights, and those thresholds that we were talking about, right? So the performance should be a function of the desired function and the calculated function. So how are we going to compute some sort of loss or error, right? This is just one example. I'm not saying this is what everyone does, but we're going to take some inputs, we'll run it through the desired function, if we had it, then we'll run it through our function approximator, or our neural network. We'll find the difference of those things and then maybe square it or something like that to get some sort of loss function. And the best possible performance would be where that p is equal to 0, right? So when our computed approximation exactly matches this function that we want. And so what we want to do is attempt to minimize that error value p. So what we have to do is adjust the weights somehow. So I'll explain this as I go. Let's say we have some weights W1 and W2. What we see over on the right here is what we call a performance contour. So what this means is, let's say we could run our neural network for every possible input value of x1 and x2, right? So what this would map is, let's say this is like a topological graph where the best possible value might be right here in the middle, okay? And then as we move further away from this, the error would get more and more, for example. So at any given time, we are at a given W1, W2. So we might be up here in the top right, for example. What we're going to do is compute the error and try and find the direction that those x1 and x2 should head in to find the optimal W1 and W2, okay? So we're right here, for example. If we had some way of telling, we should head more in this direction, so then our next W1, W2 are right here, then our next one is right here, our next one is right here, our next one is right here. So there's all sorts of methods that we may be able to do for this, like hill climbing, all sorts of different stuff, but the way that we typically do this is with a method called gradient descent. And what gradient descent is trying to do, there will be no questions on the exam about gradient descent. I just kind of want you to know how it works without knowing all of the math. But basically, if we have a function, we are currently lying on some function. Like, for example, this was the 2D view of that. This is sort of the 1D view of this, where we're at a particular point. If we have this convex function, for example, we might be able to figure out the error between our approximated value and the actual value, and then find the direction that we should head in. And what we do is we have some starting point, and then each iteration we converge eventually to some local minima, right? So just like, so the way that we did this with, why can't I think of genetic algorithms, is through this process of artificial evolution, but the backpropagation in neural networks typically uses some process that's close to gradient descent. Now, there are literally neural net implementations that actually use genetic algorithms to update the weights, right? Whether or not they are more or less powerful, probably not quite as powerful, but it's something that can be done. So whatever you can do to update the weights to get closer and lower this error value, go right ahead. But I'm just sharing that one of the more popular ways of doing this is through gradient descent. And what you do eventually is you get to some local optima. So just like genetic algorithms and evolutionary computing can get stuck in local optima, so can neural networks. Okay, it's not always the case that they reach this global optimum. They can often get stuck in local minima, just like this. So if we wanted to animate this, it would look sort of like this. So we have this line, we are trying to update the weights. Here is the possible space of values, and by some form of gradient descent, we are optimizing our value so that it gets closer and closer to this local optima. And what that's doing is changing this line to be closer and closer to the true line. Let me just show that once more. Yeah, so the loss goes down, and we get closer and closer to approximating that function. This animation comes from this website called Backprop Explainer. I highly recommend having a look through this. It's an excellent website with lots of cool animations, and I'm using 2 more of them in the remainder of the lecture. Now, I will not ask any of the math of this, like what, how do you calculate the partial derivatives that are necessary for a gradient descent. This is not a calculus course. But just knowing this process could be some sort of question on the exam. So the way gradient descent works is we calculate some sort of error function, we calculate partial derivatives, and then we update the weights based on the values of those partial derivatives. I'm not getting into it because I'm not particularly concerned with the math, but the important thing here is that because gradient descent relies on deriving, then what do we need? You know, hopefully we've all taken a calculus course. When does derivation work? Only when the function is differentiable, right? So what are we going to do? Is our function differentiable? Well, let's have a look at our neuron. What part of this might be an issue? Maybe the step function, where we instantaneously go from one value to another value based on an if statement, right? So this process of thresholding is not differentiable. So this early form of the perceptron, the artificial neuron, is not differentiable. So the first thing we have to do in order to make this a more modern neural net that we can use backprop with gradient descent on is to remove that thresholding somehow. Okay, so let's get rid of the thresholding. So thresholding makes our function non-differentiable, and so it's annoying to compute. So ideally, we want our function, we want to get those thresholds out of here, right? So we used to have a function of x, w, and t. We're trying to eliminate that t. How can we do it? Enter the bias neuron. So over here, this bias neuron just has a value of 1 all the time. So we're going to add an additional neuron to each layer that just has a value of 1. And what this does, it has a fixed value of 1, and this is going to have an effect which is similar to thresholding, but it ends up being easier to compute. Why? Well, this is the diagram of when we were thresholding. So we take this dot product and we compare it to this theta threshold, right? So this is greater than equal to 0. But what we do when we have a bias neuron, it gets its own weight, okay? So instead of comparing the dot product to the threshold directly, if we have a bias neuron with 1, then through this process, what this is going to do is figure out the threshold for us, right? So down here, where it was the dot product greater than or equal to threshold, now we have the dot product minus the threshold greater than or equal to 0. But because this has its own weight, then this will be figured out. We no longer have to calculate these thresholds. This will be part of this process. Okay, so that's the first part, is getting rid of that. The second part is somehow smoothing that step function, okay? So the step function is non-differentiable. So what we do is we apply a sigmoid function to approximate the step function, but remain differentiable because it's smooth at all locations. So we have a step function over here. This is what the step function looks like. Maybe it goes from 0 to 1. We could approximate the step function with a sine function, not sin, but sign, which goes from -1 to 1. But unfortunately, that is also not differentiable. So what we do is we choose to approximate these type of functions with a sigmoid function. And so the sigmoid function smooths it out while giving you similar values. Okay, so the values are not exactly the same at every possible step, but it is very, very similar, and now it's differentiable, which is what we want. And there are many, many types of sigmoid functions, and if you've ever had to run a neural network for whatever reason, you've probably had to choose between tanh or ReLU or x over 1 plus x. There's lots of different sigmoid activation functions that you can choose from. And so this is why that's there, is because in order to do gradient descent, we would have to have a function that we can differentiate, and that's why we do this. All right, so the improved neuron now looks something like this, where we have our real valued inputs, our real valued weights, plus the bias neuron with its weight. Then those are, the dot product of those goes into a smoothed activation function, and then we get some output. And so this was the particular activation function that was being used for this example. Okay, so now we know how the neuron works. So the neural net structure then is just an input layer, an output layer, and some number of hidden layers in between, which we already talked about. A common structure for neural nets is, as I already mentioned, it's called fully connected. If we start with a fully connected network, then what will happen is any weights or connections or input variables that are not important, those weights will just get really, really low and not be part of the calculation, right? So let's say, I don't know, if we were trying to see how much weight somebody could lift, right? We might put input variables like bicep size or height or nutrition value, but then we may have eye color, right? And eye color probably has nothing to do with how much weight you can lift. And so all those other ones, which may have an effect on that value, would have high weights versus the ones that didn't have much input value would have low weights. So that will figure it out. But the important thing is the network could have an arbitrary structure. And it turns out that the fewer connections you have in a network, the less time it takes to do the training because there are fewer weights, right? So the fewer weights you have, the less time it takes to train. So if you could get away with using a smaller or less connected network, you would want to do that if possible, because it would just, it would take less time to train. And so there's a lot of research out there. For example, there are things that let's learn the structure of a neural net via a genetic algorithm. So this is crazy how we can combine all of these things together, right? So picture a genetic algorithm where the genotype are all the connections between the neurons that we have. And then you can have the fitness function be the error value, right? It's all like, all these can tie together if you want to. So in the end, what we get is a process like this. We have a neural network which feed forward computes some output. So for example, this one here from the same backprop explainer. I forgot, I wanted to set this to loop. So what we get is over time, the function approximation gets better and better and better, and our error value goes down. That's what we want, essentially. Another example of classification. Here we are, say, learning the value, learning to predict the output of handwritten characters. So your network structure for something like this may be, for example, the input layer might be the 1 or 0 pixel for each pixel in this image. So here we've got 784, so I can't remember what the size of the image is. But each of those pixels goes in as inputs. Then we have some number of hidden layers. And then the output here, instead of being a single number, like the last example here, when we're doing classification, sometimes what we want is to have one output for every possible thing that we want to classify, okay? And then here we would say, okay, the one that is closest, or the output that's highest, so if this output value here of 4 is highest, then we most likely think that this input number is 4, okay? So the structure of these neural networks, how we choose the inputs, the hidden layers, the outputs are important. And there is a video here that I have actually put as a watchable lecture. So this is an hour-long video, and it's a guy going through and coding a neural network from scratch in C++. The fact that it's in C++ doesn't matter. They're just, that was the video. If you've used JavaScript or Java or any other programming language, you'll be able to follow along with this video, no problem. And so this process of going from inputs to a fully connected network to some outputs, learning how to train that, etc., from scratch, that is this video, and that's on our lecture schedule as a lecture that I want you to watch. And this video could be on the exam. I will mention in a post about the final exam the type of things that I could want from this video, but please watch this video before the final. What we're going to do now for the remaining part of this lecture is go to this website and look at the neural net demo, because it's really, really cool, and it drives some of these points home, at least to me. So this is the extremely small text. Let me see if I can zoom in a little bit. I can't zoom in much. Okay, so I highly recommend you all go play with this, at least before the exam, because it's really cool. So what this is, it is TensorFlow's online playground to let you see what happens when we're training neural networks. For these examples, what we have are different data sets that you can select over here. And these data sets are classification data sets where we have some number of blue points and some number of orange points. What those mean doesn't really matter. What we're trying to do here is just build a classifier with a neural network that separates the plane into the region of blue points and the region of orange points. So, for example, if I select this one, and I'm going to just make it a little bit smaller so I can actually fit everything in, and then I hit this button with all of these parameters, which I'll just leave the same, eventually what we get is this trained classifier. Okay, so you can see here that now this has correctly classified all of the blue points from all of the orange points. Just need another sip. Okay, so this demo is really cool because it lets us select different data sets. It lets us transform the data before it gets passed into the neural network. It lets us add different amounts of hidden layers, neurons to each layer, etc., etc. So for example, if I gave you this data set of points, you could probably now tell me how easy or how hard it is for a neural network to classify these sets of points, right? So if I look at, okay, yeah, I can draw a line through these, right? So one of the most important things when we're trying to run a neural net is to try and decide on the structure of the neural net. So for example, now I've got 3 hidden layers. I've got 3 neurons in the first one, 6 in the second one, 2 in the last one. If I hit classify, oh look, it's instantaneously classified this. But that's going to take a lot more computation based on the complexity of that structure. So who can tell me the simplest possible structure that I could have to do this classification of points? I see, okay, yep.
Just draw a line.
Yeah, so how many neurons and hidden layers would I need for that? Yeah, so let's look. Let's go down to the simplest possible neural network. Input layer, 1 neuron, 1 hidden layer, output. Classified, done. Instantaneous, really cool. Okay, let's go to another data set right here. So this one, I can zoom in on this. This data set looks like we have a bunch of points in this circle and then a bunch of points outside that circle, right? So let me very quickly ask, is this a linearly separable problem? No, right? I can't draw a line through that. It's trying to find a line. It's doing its best to find the line that minimizes the error. Okay, how about if I add another one? Well, now it's going to draw 2 lines. And what we'll see is it's trying its best to split up that plane into sections of blue and orange. But because we are humans and we know a little bit about geometry, what's the minimum amount of lines I would need to encapsulate some sort of space? 3, right? Because 2 doesn't encapsulate a space. It's always open. So let's just see. Let's add 1 more neuron. And what shape should this probably form? Triangle, right? So let's do it. Look at that. So we've got a little bit of smoothing here based on the weights, but essentially what we've done is we've learned a triangle around this circle, right? Anything else I do, if I put more neurons here and like make this super crazy, yeah, it'll still find it, but this is going to require a lot more compute than what we just did with the 3. So if you know exactly what you can do to classify like the minimum amount you need to in order to classify something, I would recommend using that architecture. Now, what's something really interesting about this data structure? Well, what if we transformed the way this data is represented before we pass it into the neural network? Can anyone tell me a way that I could represent this data so that we might get a simpler neural network to do this classification for us? Yep. Sure. So polar coordinates, meaning that we are representing our points instead of just x, y on the plane, we're going to have some angle and some radius, right? Because as we can see here, this, and of course, if we add more points to this data set, it may not follow. But as of right now, we can kind of separate this, these two data points. We wouldn't even need polar coordinates. We would just need the radius, right? So the distance from the center classifies these two data sets, right? So look, anything shorter than this, or less distance from this, less distance than this from the origin is blue, and anything greater than that is orange. So what can we do? Well, let's come over here, and in the inputs, this is x times x1 times x2. And so this is essentially the distance squared from the radius. So we've transformed our data, and now what we can do is that if I now have this data space where I can draw a single line to separate the two values, now only one neuron is needed to do that classification. So whenever you use a neural net for something, think of the simplest possible space that you could use to represent that data before passing it into the neural network, okay? Now, this one up here, someone suggest me real quick a structure that I could use to classify these points, where I sort of have these four quadrants. Anyone? How many lines should I have? Yep. I'm just saying, how many neurons should I try? There's no wrong answer, just the number of neurons. Maybe 4, I'll try 4. Maybe 4 lines would be able to do this. Let's just have a look. Right? Because if I'm able to chop this up into 4 sections, then that's what I can do. But look at this. Another really cool thing about this visualization is that it shows us the pattern that's being learned. Okay? So right here, this is showing what this neuron is doing to the classification. It is chopping orange down here, blue up here. This one is doing this one. This one is doing this one, and this one is doing this one. And then some combination of those is able to classify these points. But what I want to show you now is what new layers do. So we can all visualize what happens within the same layer if there's only one layer. But what happens when we add new layers? Well, what is going to happen here is that this is a pattern of the input space, and then this layer is going to be a pattern of this input space. So we're forming patterns of patterns of patterns of patterns as we add new hidden layers. So let's just look at this. So what happened? Over here, we classified based on top and bottom. Here we classified based on left and right. And then based on those two, we can then chop those up into these and then use that as the classifier. So essentially, every new layer is a new level of patterns based on the previous layer. And that is, in a hand-wavy, high-level way, what is happening with these deep neural nets. Okay, now you've got other stuff like, this spiral, which is very difficult to classify. It turns out that, there are patterns of inputs that you might be able to use to classify this, but it's not easy, and I'm not going to spend too much more time on it. I just wanted you to get the feel for this, but please go play with this. It's really neat, and it really helps you to understand what's happening in neural nets. Okay, really quickly, I'm going to go through last couple of slides here. I'm not going to full screen it because the Mac output is strange. So some applications that we have for neural nets, function approximation, that's what they do. They approximate functions. And these days, you can get some pretty damn complex functions that you want to approximate, including a function of how to play checkers, right? Like, it's crazy, the type of functions that they have. We just saw an example of image classification. They're really good at that. Something else we could do is maybe learn a heuristic function, right? So if we're looking at A star, for example, maybe we've done a bunch of examples of A star, and now we pass into the inputs the 2 points on the map, and the output would be a guess at how much distance is left remaining to the goal. And so if we learned a heuristic value, maybe we could use that in search to do search faster. It turns out that in a very hand-wavy way, this is how the poker people ended up doing things. So based on what cards they have in their hand, they wrote an evaluation function to say how likely they are to win or lose a hand based on the cards that they have in their hand and the cards on the table playing poker. So they used deep learning to learn an evaluation function and then used search, a form of search, based on that. AlphaGo, it used two different types of networks. And another video that I want you to watch on your own is the AlphaGo movie. So that's another lecture that we won't be having here. And that will be on the final exam. What AlphaGo did was combined deep learning with heuristic search. And so two networks were trained. One was the value network. And so with the value network, what they did was they fed it in a bunch of board positions. So they got a bunch of replays from games and also from self-play. But basically the input value was what's the current state of the game, and the output value was who ended up winning that game. So with high accuracy, they could just look at the state of the game and say who's going to win from this state, right? So imagine having that powerful of an evaluation function for assignment 3. I can just tell you who's going to win if you play well from this state. And so they used that as their evaluation function. And then they also trained what's called a policy network. So the input to that neural network was, again, the state of the game. And the output was, how likely should you be to take any of the moves on the board, right? So what are, for example, the top 3 actions that I should take or consider at this state of the game? So what it did was looked at a bunch of games, saw what human professionals did, and said, okay, if it's this state of the game, you should either do this move or this move or this move. And then when they went to do the search to find the move, they didn't have to look at all 300 possible moves that you can do in Go. They just looked at the 3 to 5 moves that the neural network said it should probably look at. And so it dramatically lowered the branching factor, which meant it was able to search much deeper in the tree. And it turns out that later on, they just did it all with reinforcement learning. So reinforcement learning in AlphaGo 0 turned out to be very, very powerful. But we're going to watch that AlphaGo movie, not in class, but on your own, and you'll see. It's a really excellent movie. Has anyone seen it before? It's really, really cool, and it's quite dramatic, and it's like way more entertaining than you think it'll be. You could also learn from replays, so that's what they did in the first version of AlphaGo. And learning from self-play, so once it had learned from the replays, then it started playing against itself. And once it got better, then playing against itself means it got even better, so it got better and better and better in this positive feedback loop. Also, make sure you throw in some random bad moves here and there so that it learns what to do in situations that aren't particularly good. Yeah, I think I already said what this did. So here's some possible exam questions. Explain and compute the output for a TLU. Find the parameters for a TLU for a specific function. Explain linear separability. Compute whether a simple function is linearly separable. Describe the structure of a neuron or a neural network. The implementation of the neural network and AlphaGo videos. Those can be questions on the final. I will not ask any of the mathematics of gradient descent, but there could be a question on the general theory of what is backpropagation and what is it doing. Okay, so that's the lecture. That's a brief introduction to neural networks. Did you have a question? Yeah. Yep.
Link for the AlphaGo videos?
It's on the spreadsheet. So I actually have lectures. I'll go. Actually, let me do that now. So here, if we look at our schedule, so this is today. Next, I want you to watch the neural net implementation video. So there is no lecture in class on Tuesday. I'm not playing that video here. Just watch that on your own. Then we have the final deep neural network video that is an in-class lecture. And then the last thing for the year is for you to just watch the AlphaGo movie on your own. So we only have deep neural networks remaining. That's the only actual in-class lecture. And I don't have these here right now because I forgot, but those links will be up shortly. So those will point you directly to those videos. Okay, Really quickly, at the end here, I want to show you some improvements that I made to assignment 5 since it was released. And what I did was I included the cliff. So this is the cliff example. And if you see here, I also print out the reward values for any terminal state on it. So here we have negative 100s all the way over until we get to 0. We also have algorithm selection, so you can select between SARSA and Q-learning. And one other thing, which actually doesn't really add, it adds like one line of code total to your solution, which is choosing between exploring starts or returning to the start state. So what I've done is for every environment, I have now included a predefined starting state. So if it's exploring starts is selected, it means that you choose a random location on the map to restart at. If it is return to start state, then you just set the state to the start state. So I really quickly wanted to show you, oh, and I also changed the graph, but I'll show you that in a second. So let me really quickly show you SARSA return to start state on the cliff. So if we learn here, if we pause it, we can see that the theory matches the practice. SARSA will take a safer path, okay? So here, when SARSA is incorporating epsilon greedy into its value function, it is telling you to get away from this state. Go up, don't come near this state, because it's incorporating the value of possibly falling off the cliff into its learning. Whereas if over here I select Q-learning and I do the same thing, Q-learning says, I don't care about that, just go straight across next to the cliff. Okay? So we're able to reproduce the figures in the book, which is always great when we can reproduce that. Now, really quickly, I want to show you this average reward per terminal, that graph that I've gotten down here. Let me let that converge a little bit. So what happens is I calculate the total reward that we've gotten for the whole training session, and then I divide that by the number of terminal states that we hit. So what this is it's saying what's the average reward we got per, not episode, but per terminal state. This is the graph that we looked at in the slides. So for Q-learning, the average reward per terminal state ends up being about negative 32, right? And the reason it's negative 32 is because we hit those negative 100s all the time, right? Because in the training, we're still using epsilon greedy, and Q-learning is having us go right across next to the cliff. So during training, well, let's have a look at what SARSA does. If we go to SARSA and we toggle iteration, instead of negative 32, SARSA actually does better. It gets more reward per episode during training. But if we look over here, the policy is obviously worse. Because once we take this model and we take it to our deployment, right, and we're no longer doing exploration, then SARSA's is going to be worse. So this is just, we've replicated the theory that I had in the last slides, where I said SARSA is going to show better online performance during training in this, but Q-learning is actually going to have the better overall policy once the training is done, okay? And we can also look at other examples. So if I have SARSA here, you know, training versus Q-learning, the values end up actually being much closer. Why? Because this is kind of simply a pathfinding problem. Oh, I forgot to, one second. This is return to start state. I wanted exploring starts. So this one, SARSA with exploring starts. What is this value? It says -6, approximately -6. If I switch this to Q-learning, it's about the same. So you say, why are they the same for this one, but not the same for the cliff, right? It's because in this one, every action has the same reward. There is no cliff that SARSA is successfully avoiding. But if we did have some sort of cliff in this example, then SARSA should perform a little bit better because it's taking those safer paths over time. But that's just during training, right? The eventual policy that Q-learning got, because it's saying what's the best thing I could do at the next state, would be a better overall policy, just not during training. And really quickly, the changes to the code are very minor, but I just wanted to go over them. So now what we have is we have an algorithm parameter here in, let me make this a little bit bigger. So this .config has an algorithm parameter and it has an exploring starts parameter. So the algorithm is either going to be sarsa or a Q-learning string, and exploring starts is either going to be true or false. So if we come down to where this matters, exploring starts is going to matter when we've reached a terminal state. So if this is a terminal state, when I explained the assignment the first time, I said just set it back to a random clear tile. Now you're going to check if exploring starts is true, do that. Otherwise, if exploring starts is not true, this is literally the line of code that you have to do. So this .state is equal to this .env.start state. So that's a new variable that I put into the environment. And then the other place that has changed is down here, where when you go to update the value, you're now just checking to see if it's sarsa, do the sarsa update rule. If it's Q-learning, do the Q-learning update rule. Whereas before, it was just do Q-learning, okay? And remember that with sarsa, you have to get the value of the actual action you would do at the next state. But the cool thing about this assignment is you already have a function that's done that for you. So I say here, note, in order to get the action at the next state, you can use that function. Select action from policy at the next state, which you already have. Okay, so use that for sarsa and you're basically done. And that's it. Nothing else has changed. Just two new variables and a much better user interface that lets you debug it a little bit easier. So in the marking, we are going to be running the Cliff example. So make sure that you test to see that sarsa with return to start state is performing better than Q-learning. Okay, and that's it. Yep, question.
When we were talking about it in the class, I was under the impression that sarsa would take the furthest path away from the cliff. It seems like it's just taking the second path away from the cliff.
So
just because you're not training it very long, or?
So the question was, why doesn't sarsa take us all the way up? That depends on these values. So if there's more exploration, then it's more dangerous, and sarsa will take us farther away. So if I bump up epsilon to say 30 or 40%, it will start moving us farther away, right? It's just that the math happens to work out with the values of alpha, epsilon, and gamma that it thinks moving up one is fine. Yeah. But yes, it's a very good question, and this is the answer to that question. It's all depending on those parameters. So I wasn't exactly sure what the parameters from the book were. Maybe you could actually find those and plug them in and see if it produces the same values. Okay, great. Thanks.